Now we're going to take a look at applications of vectors, which everybody's favorite, word problems. Vectors have really useful applications when we're talking about the force on an object or the force of an object. So our first example is Jeremiah and Eli are both tugging on the toy box with different force and in slightly different directions. Our question is, what is the resulting force on the toy box? It makes sense to think about this as the addition of the two forces is what is moving the toy box. So we're going to figure out the component form for each vector of force and then combine them to get the resulting vector. Now remember, the direction angle is from the horizontal, and bearings, like I gave you on this one, are from the vertical. So the first thing we need to do is find the direction angle from the positive x-axis instead of from the positive y-axis. Jeremiah is pulling in a direction of north 20 degrees east. So if we subtract that from 90 degrees, it's a 70-degree direction angle from the horizontal. Eli is pulling in a direction of north 65 degrees east. Subtracting that from 90 degrees, his direction angle is 25 degrees. Putting these into component form, Jeremiah is pulling with a force of 30 pounds. We're going to take the cosine of the direction angle and the sine of the direction angle. Combining that with Eli's force of 10 pounds and his direction angle of 25 degrees. We will distribute the 30 pounds through. And we'll distribute the 10 pounds through. And then we'll need to add our x components and our y components. So I'm going to add 30 times the cosine of 70 degrees plus 10 times the cosine of 25 degrees. This gives me an approximate x component of our resulting vector of 19.324, rounding to the nearest thousandth. For the y component, I took 30 times the sine of 70 degrees plus 10 times the sine of 25 degrees to get a result of 32.417 for the y component of our force vector. We were asked to find the magnitude and direction of the force vector. So to find the magnitude, we use distance formula. We end up with the square root of 19.324 squared plus 32.417 squared. Taking the square root of that value, I punched everything into my calculator. I just used parentheses around what's under the radical to get a magnitude of 37.740. To label my magnitude, I will use the same label that was given to me in the problem, and that was pounds. Finally, finding that direction angle. Tangent of theta equals the y component of our vector, which was 32.417, over the x component of 19.324. Taking the tangent inverse of both sides, we get a direction angle of about 59.2 degrees. Next, we're being asked to find the force required to keep a barrel from sliding down a hill. We have a 12.5 degree incline. We've got the barrel on the hill. The force of gravity is the weight of the barrel. So here's our force vector. I'm going to call this BA. We need to know how to prevent it from sliding. This AC vector is heading in the same direction as the hill. And then we've got our BC vector, which is the force of the barrel against the ramp. We have a 90-degree angle at C. Because of the way that we set this up, AC, again, is parallel to, I'll call this W, WB. The direction of the ramp, AC, is parallel to that because the force to keep it from falling needs to be in the same direction as the ramp. I'm going to call this point where the BA vector, which is supposed to be straight down. I'm looking at my line and it seems a little skewed. BA is a vertical line forced down. That's the weight of gravity, which is of course always pulling straight down towards the ground. If you think about rotating the ABC triangle, it is similar to the WBD triangle. And the way that they are similar, if you remember from geometry, you have to keep the coordinates of each triangle lined up so that corresponding angles match each other when you name them. So I'm naming triangle BWD is similar to triangle ABC. Looking at it this way, angle D is the 90-degree angle in our first triangle, and angle C is the 90-degree angle in our second triangle. So those angles need to be lined up. Also, angle W is the 12.5-degree angle, and you can see that angle B is the 12.5-degree angle in the second triangle. So those need to be lined up as well, leaving us with B and A as angles lined up for the last vertex. Using these similar triangles, we now know that this angle up at B is indeed 12.5 degrees. We know the force vertically is the weight of the barrel, which was 280 pounds. And we're looking for AC, that force needed to keep it stable. Because it's a right triangle, we can set up SOHCAHTOA. Sine of 12.5 degrees equals opposite, which is that x, the magnitude of AC, the length of that vector, over the magnitude of BA, which is the 280 degrees, or the weight of the barrel. Multiplying both sides by 280, we get a force needed of about 60.603, and again, labeling the same units as in the problem, pounds. I feel like that last example is a little bit complex to keep track of, so I set up a general example for you of when gravity and an incline are combined and we're looking for different forces. So this picture is completely labeled the same way I labeled our picture in the example, so you can keep track of the different forces acting on that object. One final example, we're looking at the velocity of a plane and its direction, and then the force of wind pushing it slightly off course. In this case, we don't know the velocity of the wind. We know where the plane is trying to go. That's the first two pieces of information. And we know where the plane is actually going. That's the second two pieces of information. Knowing those, we can figure out the force of the wind. First of all, the plane is flying south 36 degrees east, meaning 36 degrees east of south, with a speed of 540 miles per hour. We'll call our magnitude 540 and just assume it's been traveling 1 hour for the sake of ease for working with this problem. But the wind is pushing it slightly off course. We'll call this W since it's the wind vector. And it is pushing it to an angle of 44 degrees, and it slowed its speed down to 500. Now that I've added those arrows in for you to show you the direction the vectors are heading, we can look at this picture and recognize that we have this vector, we'll call it U, and our V vector, where the plane is actually heading. The W vector is a result of the V vector minus the U vector. Thinking about how we've been setting up our pictures for subtraction, we're heading from the U vector towards the V vector. So the U vector is the one being subtracted, and the V vector is the one we're starting with. We need one more thing before we can set up these vectors in component form, and that is again that angle that it makes with the horizontal. We have angles with the vertical, so we need to figure out how far around from the positive x-axis we rotated. My picture is getting a little bit messy, so I'm going to start by pulling out our first vector. This is my u vector that had a 36-degree angle with the vertical. Now remember, we're starting from here, so we have to figure out how far around we went to get to the vector. The angle I just made is a 270-degree angle, plus that additional 36 degrees gives us a total of 306 degrees for our u vector. Doing the same thing with my v vector, it was pushed off at a 44-degree angle. Thinking about the fact that this is 270 degrees from the horizontal, if I add those two together, I get a total of a 314-degree angle. So now we have the information we need to take our v vector and subtract our u vector. Our v vector had the magnitude of 500 and an angle of 314 degrees. And then we're subtracting our u vector, which had a magnitude of 540 degrees and an angle of 306. That's a cosine. As this video is getting a little bit long, I'm not going to show every step. This is very similar to the steps that we took in example 1. Distribute your magnitude and then use your calculator to combine the x forces and the y forces to get the component form of the result. I called my resulting vector W for the wind, and 500 times the cosine of 314 minus 540 times the cosine of 306 gives us an x component of 29.925. 500 times the sine of 314 minus 540 times the sine of 306 gives us a y component of 77.199. The question was the magnitude and speed of the wind. Once we have our component form, we can find the magnitude by using our distance formula. That'll be the square root of 29.925 squared plus 77.199 squared, which gives us an approximate magnitude of 82.796. Labeling it the same way it was labeled in our word problem, our magnitude was in terms of miles per hour. Finding that direction angle, we'll have tangent of theta equals that y component over the x component. Taking the tangent inverse of both sides, we get an angle of about 68.8 degrees.